Hello chaps, this is Mr. Pope from Grammar School for Boys, and this is the first in hopefully quite a long series of accelerated maths. Today we're going to be looking at surds and indices, and the main reason I wanted to talk about them first is they're pretty important. And before I dive in too much, I just want to give a rationale of why I'm doing things in a certain order and why I've chosen to do this. First reason is there's quite a lot of students in year 11 and year 12 who might be a bit apprehensive. As of the time of the recording, it is what's the date today? It is the 12th of April, and as a country, England is in lockdown due to the COVID-19 virus, and quite a lot of students are a bit apprehensive as what's going to happen, how is this going to affect their studies, and will they be left behind. In an attempt to remedy that, I'm doing a series of lessons with material taken from the edXL A-level books and various other sources to help students get all the stuff they need to know instead of watching endless videos and just generally getting a bit lost. And the reason I've chosen these topics in order, which are all available on my Google Classroom link. Unfortunately, that's private, but only people in that Google Classroom link can see, is I feel the edXL course do things in a bit of a funny order. I don't think maths particularly has much of an order. Well, in terms of complexity, it does, but there's quite a lot of topics you can do interchangeably, and it's very difficult to advance in depth in one particular topic without running into something else. So this is my interpretation of how I see young people from the ages of 14 to 15, 16 being good at maths at university level. It is going to be difficult because there's going to be a lot of new content thrown at you at a fast pace, and modern pedagogy, never be able to say that word correctly, modern pedagogy does state that, well, the general line of thought is you should break things down into bite-sized chunks, and I agree. If you're trying to teach students to a certain level and coach them for exams, I think, that probably is the way forward. But in my very limited experience, I think there are skills that you can gain from having things in one big block, mainly patience, perseverance, attention, being able to be mentally resilient and flexible, seeing the bigger picture. One of the biggest criticisms of school is like, well, what's the point of learning this? And usually if you're only learning things in bite-sized chunks, I don't think you're going to see the big picture as much. The other thing is for university study, which essentially, for academic mathematicians, vying for university places and taking their academic career to the next level, that's really what's important. A lot of university lecturers will kind of yammer on for about an hour or so, and maybe that's a poor way of saying it, but because when I was there, and I've been at university for 8 years, I found it incredibly fascinating. There's even if it was a lecture on something I wasn't particularly interested in beforehand, I think the fact you're in a room with somebody at the top of their game, the leading expert in their field, and they're giving their expert opinion to you, I just think it's magical. And I just don't think, if you prepare students to only be able to digest information in 10-minute bite-sized chunks, they're just going to be in a real world of hurt when they get to university. But anyway, right, so that's my 5-minute ramble. Today we're starting with surds and indices, a bit of basic algebra, and just to mix things up, I'm going to throw some complex numbers in there at the end, with a bit of logarithms as well, and hopefully you'll see the bigger picture of why I've done that. I think the main thing when you go to university is they're for mathematics anyway, they're going to be wanting students not necessarily to be familiar with complex numbers, but at least be able to pick it up fairly quickly. And I think if you're really familiar with them in the get-go, you know, your first term or so or semester is going to be pretty easy. But anyway, what is a surd? Now, they're called various things around the world. Some people call them radicals. But essentially, what I'm going to be talking about is whenever I'm dealing with the square root of some number k. And that really could be anything. And more generally, I'm talking about the nth root of that value. And generally speaking, you know, when we just leave it as something like this, root of 25, we're talking about the second root of 25. And essentially we're saying if this number is 2, then I want 2 slots, and I want to know how many times, what number, it's just the same number in these boxes. These boxes must be the same such that they equal 25. And here, this is clearly 5. 5 times 5 is 25. But argument could be said that -5 multiplied by -5 could be an answer. And when we look at the complex plane, we'll be looking at multiple roots here. But for the purposes of surds, if I was going to be talking about root 9, I would just simplify that down to 3. And you're probably thinking, well, how do I know when to just do this? Well, the operation of square rooting or rooting is when you introduce multiple branches. For example, if I write root 9, that is just 3. But if I was trying to solve x squared minus 9 equals to 0, then I'd follow that through and make x squared equal to 9, such that when I square root both sides to solve this, I get x equals the square root of 9. And thus, by doing that operation of square rooting both sides, I've essentially introduced 2 potential branches of solutions, and it's not entirely clear or not whether the positive or negative root of 9, which is positive or -3, which one of them is actually applicable anymore. So really, it's I guess in video games it's called context sensitive. Depends on the context of the question. When we're just dealing with surds, we're just going to leave it like that. Positive. We normally take the positive branch. And in general, when we're dealing with surds, we let this value k we let k belong to the set of positive integers. Okay, so this means belongs to. It's a bit of set notation, and this italicized z just means the integers, and this little plus up here just means we're talking about the positive integers. So if I was to write something like this, well, in actual fact, z plus, I suppose we could have it as z plus, but really what we're talking about is q plus, and this is quotient or the rational numbers. And we're going to be talking about this idea of rational numbers later on. But for example, if I wrote, let's say 20.25, I mean, yes, that is technically a surd, but as mathematicians, we don't really want to write it as that. We'd probably write it as the square root of 81 over 4, or just the square root of 81 over the square root of 4. And by doing so, you can probably tell straight away that root 81 is 9 and the square root of 4 is 2. And, you know, in the context of the original question, root 20.25 actually turns out to be 4.5. And notice how it's not immediately obvious what the square root of 20.25 is looking at it as a decimal number. But when we convert it into a top-heavy fraction, because it is a rational number, then, you know, the simplified form is definitely a lot more obvious. Okay, so that brings me on to my next bit. What are the things you can do with surds? Okay, and how do we simplify them? And to start with, I'll look at the simplification bit first, because that's probably one of the most important things. So, in general, if I have an nth root surd, and there's some value inside there, then what I want to do is I want to take the nth root, and now I have to split it up into two numbers. One of them I'll call a, and that'll be to the power n, and that'll be multiplied by a different number b. And ideally, we want to make this power of n number as large as possible. So what do I mean by that? Let's say I've got the square root, I won't put the 2 there, the square root of 108. Okay, now because I'm talking about the square roots, I want the largest square number that's a factor of 108. Well, square numbers, we've got 1, 4, 9, 16, 25, 36, 49, and so on and so on. Now, I think 4 goes into it. 4 times by, well, 4 lots of what is 108? Is that 27? But 4 is obviously 2 squared, but is that the largest? I don't think so. In actual fact, I mean, you could do this. The point is, if you don't pick the largest square number, then you haven't fully simplified it, and you're going to have to do it again. So let's try and get it right the first time. What's the largest square number that goes into 108? Well, I think it's 36, and it's actually 3 lots of 36. Now, because 36 is 6 squared, I don't think I can get a larger square number out of that. So this can be split up as the square root of 36 times by the square root of 3, and the square root of 36 is 6. So, in actual fact, 108 square rooted is the same as 6 lots of the square root 3. Okay, what we're saying is I've got 6 lots of root 3, just in the same way as I've got 6x. There's a number in front of that, it just means I've got 6 lots of that thing. Fine. Let's take one where it's not particularly obvious what you need to do. So let's try the cubed root of 250. So what's the largest cube number? So this is the n squared numbers. The cube numbers, well, I've got 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 5 cubed is 125, 6 cubed is 216, 7 cubed is 343, so on and so on. Ooh, 125, that works out. So this is clearly going to be the cubed root of 125 times by 2. So this is going to be the cubed root of 125 times by the cubed root of 2. And the cubed root of 125 is 5, so it's 5 times the cubed root of 2 is the cubed root of 250. Okay, so being able to simplify things like that, you know, really has to be nailed down. This is example 1, and let's say this is example 2. And yeah, that just, you know, that really needs to be bolted down. Yeah. Okay. So now let's talk about. Let's highlight all this stuff. So all this was the simplifications, Now let's talk about operations with the surds. So what operations can we talk about? Well, okay, first of all, if I've got root A and I add root B, then that is just root A plus root B. As long as this is fully simplified, there's not a lot you can do. If A and B are different, i.e. A is not B. Okay, so have an example of that. Let's say I've got root 21 plus root 17. Well, there's no square numbers. There's no square numbers that go into root 21 because 21 prime factors is just 3 times 7. And 17 is prime, so that's going to be broken down as 1 and 17. So because they can't simplify anymore and 21 and 17 are not the same number, then that cannot be simplified, so that just stays as root 21 plus root 17. However, let's say I try something else. Let's say I have root 18 plus root 32. Now 18 and 32 are not the same number, so you'd be forgiven to think that this is just going to be another boring example, but wait a minute. Root 18 is root 9 times root 2, because 9 is a square number, and root 32 is root 16 and root 2. And now, root 9 is 3, so I've got 3 lots of root 2, and root 16 is 4, so that's 4 root 2. I've got 3 root 2 plus 4 root 2, so that's going to leave me with 7 lots of the square root of 2. So yeah, that's pretty easy. And it's not immediately obvious looking at 18 and 32 that 7 root 2 is the case. But if you just simplify each one in turn, it kind of works out. And by the way, this addition and subtraction rule works in the same way. For example, if I'll call this example 1a, if it had been root 21 minus root 17, negative instead, then this still would be root 21 minus root 17 because they're both simplified and they don't have anything in common. However, example 2a, if we'd have had root 18 minus root 32, then this would have played out the same way. Root 18, I'm hoping you can see now, jumps to 3 root 2, minus, and root 32 becomes 4 root 2. So 3 lots of root 2 minus 4 root 2 just becomes minus 1 lots of root 2. And in general, just like x, I don't write 1 in front of the x, I just leave it as x. And I don't write minus 1x, I just leave it as minus x. So it looks like root 18 minus root 32 is just negative root 2. Okay, so addition works as you'd expect. Okay, what else can we do? Well, we can multiply. If I've got root a and I multiply it by root b, that is just the same as the root of ab. And now if I introduce letters in front of that, let's say c and let's say d here, then this is just cd multiplied by root ab. So let's have an example of this. Let's say now, previously, let's do root 18 multiplied by, I don't know, root 63. Okay, I mean, we can just do this straight away and just say it's the square root of 18 times 63, but unless you can be bothered to actually work that out, you're still going to have to simplify and it's not particularly meaningful. So yes, you can jump straight to that, but you really want to simplify. So root 18, we've seen this already, this is 3 root 2, and root 63, no stretch of the imagination, is just 3 root 7. Why? Because it's 9 times 7 is 63, and root 9 is 3. So if I times these two together, we do it as we'd expect. So we're going to have a 3 times a 3, which is a 9, And then we're going to have a root 2 times a root 7, which is root 14. Therefore, root 18 times root 63 is 9 lots of the square root of 14. That's pretty straightforward. Obviously, what you would get if you'd just gone straight in with 18 times 63 is you'd have had a horrible 81 times 14 inside of the square root, and it wouldn't have been obvious what the largest square number is there. So what was that? Example 3. Example 4. Let's have a look at dividing. So what happens if I've got, say, the square root of 164, and this is all over or let's say the square root of 24. Okay, so let's try simplifying these first. So root 24, let's do the smaller one first. So root 24 is 4 times 6, so it's going to be 2 root 6 on the bottom. Next, let's have a look at 164. Now there's nothing wrong with drawing a little prime factor tree and taking it right back to early secondary school. So root 164, I believe that's 4 lots of 41. Is that true? And then 4 is 2 times 2. And 41, I believe, is a prime. And the reason I can check it's a prime, this is a little side note, and I do lots of these in my classes. A prime check is you square root the number you're looking for, and you check for all the primes that are lower or equal to this. Okay, so what do I mean by that? So if I want to check 41, I square root 41, and I notice that root 49 is 7, and root 36 is 6. So root 41 is going to be 6 and a bit. So now all I have to do is check all the primes that are lower or equal to 6. So that's going to be 5, 3, and 2. Is 41 in the 5 times table? No. Is it in the 2 times table? No, because it's odd. Is it in the 3 times table? Well, it's 30 plus 11. 30 is in the 3 times table. 11's not. Another multiple of 3 check is you add the digits. 4 plus 1 is 5, and 5 isn't a multiple. So in actual fact, 41 is prime. So the top becomes, and the interesting thing from this is because I've got 2 2's there, I know that cancels down to 2 root 41 like so. And thus 2 over 2 just cancels. So I've got root 41 over root 6, which is the square root of 41 over 6, like so. I mean, you're quite happy to leave it like that, but we're going to be seeing in a little bit another way of writing this that's more preferred for mathematicians. We don't really like leaving things like this, although it is an acceptable answer. It's not particularly desirable. So adding, subtracting, multiplying, that kind of stuff. So let's try another multiplication one. So what's this? Example 5. Okay, let's say we want to expand. And by the way, if I've written out something, go for it. I'm going quite slowly. Just pause the video, give it a try yourself. So let's say I've got 2 plus root 3, and I've got 1 minus root 3, and I want to expand it. Well, this is just a FOIL, or just however you want to expand double brackets. Fairly quickly, 2 times 1 is 2. 2 times minus root 3 is minus 2 root 3. Root 3 times 1 is plus a root 3, and root 3 times minus root 3 is just minus 3. So I tidy this up. A 2 and a minus 3 is minus 1, and a minus 2 root 3 plus a root 3 is minus root 3. Notice how these slashes go from top left to bottom right, and these slashes go top right to bottom left. The orientation matters to me because I can see at a glance which terms I've cancelled with what. I mean, it's a style point at this. It's not, it won't penalise you, but I just find when you're dealing with something really complicated, you need to have, well, I think so. You need to have like a regiment. It's good to have like a regimented approach, and it just minimises errors really. Okay, so we can expand brackets, we can add or subtract surds, we can cancel surds. That will lead me on nicely to the next bit. I'll be posting all these as PDFs with a little bit of tidy up to Google Classroom. Okay, rationalising denominators. What is a... Okay, so what I was talking about before, when you want to, when you're dividing by dividing by surds or anything like that, you've got some kind of fraction. Generally speaking, it's been the style of mathematicians to not have irrational numbers on the bottom of a fraction. And you're probably thinking, okay, well, what the hell is a rational number? And if you're at school, it might have been the first time you've heard of it, especially if you're in year 8 or year 9 or you're 11, 12, 13-year-old and your crazy maths teacher's just talking about it. So, okay, I'm going to try and describe what is a rational number. Well, as far as I'm concerned, the formal definition of a rational number is a rational number, which is denoted by the set, this italicized Q, is such that it is all the set of numbers where I can write them as A over B, where A and B belong to the set of integers. Okay, so if you can write a number as an integer divided by an integer as a fraction, as a quotient, that's why it's called a rational number, because it's a quotient of two numbers, and both of those numbers are integers, then hooray, you have a rational number. So, for example, 2, let's have some examples. So example 2 is a rational number because I can write that as 2 divided by 1, or I could write that as 4 divided by 2, or I could write that as 8 divided by 4, and so on and so on. The list just goes on and on and on. There's no unique way of writing them. Well, a third is a rational number. That's nice, clearly, because it's 1 over 3. There's a few exceptions. Pi, that's not a rational number. And at some point, we're going to be proving that's not a rational number. And generally speaking, the square root of k, where k is not, or k does not equal some number squared, where n belongs to the integers, this is irrational. Okay, so what do I mean by that? Well, if I take, let's take all the counting k's up. Oh, geez, when n belongs to the set of integers. So this is quite a key thing when it comes to surds. If the surd is not the square root of a square number, or it's not an exact integer. So, okay, so why is that? Okay, fine. So, square root of 1, square root of 2, square root of 3, square root of 4, square root of 5, square root of 6, and so on and so on. Okay, so the square root of 4 is 2. Now, 2 is a whole number. That can be written as 2 over 1 and so on. That's okay. Square root of 1, well, that's just 1. That can be written as 1 over 1. That's okay. I'm claiming that root 2, root 3, root 5, root 6, root 7, root 8, and so on, where the square roots cannot be evaluated as whole numbers, they are irrational. They are not rational. Why is that? Well, this is quite a famous proof, actually. And you can do this for square root of 2 traditionally, but you can do this for square root of 3, square root of 5, square root of 6, and you can pretty much... I'll just do it for, let's say k. Let's say some k. And what we're going to do is we're going to prove by contradiction. So this is a proof by contradiction. What does that mean? It means that there's various ways of proving things. I'm going to go over it later, but there's valid ways of proof. Okay, mathematicians, professional ones, they spend their lives writing epic papers with really detailed proofs. One very basic form of proving things is by contradiction. And although it's basic, it's pretty powerful. And the way it works is you assume the opposites are true. So let's assume that root k can be written as a fraction, a rational number, where a and b are integers and they are co-prime. That's important, which means they're fully cancelled down. So what does it mean to be co-prime? It means they have no common factors. That is a terrible spelling of cancelled. They are fully cancelled down. So I'll give you an example of that. Let's say I've got let's say I've got 3 over 20. Now, they are co-prime. Why? Because 20 doesn't need to be prime itself, but it has no common factors with 3. That is fully cancelled down. So if the fraction is fully cancelled down, we'd say the numerator and denominator are co-prime. That's really important. So what's the next step of this argument? Well, if root k equals a over b, then it makes sense that as long as I square both sides, whatever I do to both sides, I do it equally, then this identity is preserved. So if I square both sides, I get k is some a squared over b squared. Okay, nothing wrong here. I've just squared everything both sides. And then because b isn't 0, that should be another thing, b cannot equal to 0. And that should be obvious because dividing by 0 is not a good thing. We'll be talking about that later, but essentially you don't divide by 0. That's generally a bad thing. When I multiply by b squared both sides, I get k lots of b squared equals a squared. And then you've got to think to yourself very carefully, what does this mean? Well, a squared is just a number. And k lots of b squared is a number as well. But this thing is a multiple of k. Why is it a multiple of k? Because it's k times by something. Okay, if I've got 3 times 6, I know this is a multiple of 3. If I've got 3 times 1,047,000, I don't need to know what it is. It's a multiple of 3. If it's 3 times something, it's a multiple of 3. So if I've got k times something, I know that whatever the result is, that's a multiple of k. Why is that good to know? Because that means the right-hand side must also be a multiple of k. And instead of writing multiple of k, I'm just going to do what mathematicians do. And I'm going to put slash and k, which means divisible by k. Both of these sides are divisible by k. And if that's true, we're going to let a equal some k lots of c, where c is also an integer. So in that case, a squared is this thing squared, which is k squared times c squared, which is k squared c squared. So I now have kb squared equals k squared c squared. I can divide by k both sides to get b squared equals k lots of c squared. And now we run into a similar argument. We now have on the right hand side, because it's k times c squared, this must be a multiple of k. But now I've got b squared is also a multiple of k. Can you see the problem here? We've got that a is a multiple of k, and we've got b squared is a multiple of k, which means the contradiction is they are not co-prime. This fraction has not been simplified down anymore. There was a contradiction. So there is a contradiction that a and b both divide by k, therefore root k is irrational for k not equal to a square number. Okay, and in general, you know, So so that's quite powerful. So I've got root 7. I know I can't write that as some number over some number, where those numbers are integers. Why is this so important? What's the point of proving all this stuff? Well, back in the day, we haven't always had computers. And suppose, for example, a really weird guy might be interested in what the numerical value of 1 over root 2 is. So, okay, let's suppose through, let's suppose that you know a bit of mathematics, and we'll come on to it later using the binomial expansion and various other things. But let's suppose you've managed to work out what root 2 is. And you work that out to be approximately, because you don't have a calculator, remember, you approximate root 2, you approximate it to root 2 to be approximately 1.414213562, and so on and so on. And you can keep churning this out, and that's absolutely fine. But when it comes to 1 over root 2, you're stuck with this. Okay, how do I figure that out? Well, that's 1.000000 divided by 1. Okay, how's that going to work? And the reason why that's not going to work is because this thing, it's an irrational number. It doesn't stop. It cannot be. This goes on with no pattern. If it did have a pattern, then you could use your work with recurring decimals and so on to chop it off and make it a rational number. But unfortunately, it can't. So it doesn't have a pattern, so it keeps going on. So this actually becomes impossible to compute. However, do you agree with me, hopefully, that 1 over root 2 times by 1 is still 1 over root 2? Yeah, if I multiply things by 1, that's not going to change its value. So what we're going to do is be really cheeky. Now 1 over root 2 times by 1 again, but this time I'm going to let it be a fraction. And if that fraction is root 2 over root 2, now look what happens. Root 2 over root 2 is just 1, because it's the same fraction top and bottom. So I'm going to have 1 times root 2 on the top, which is root 2, and root 2 times root 2 on the bottom, which is just 2. Now that's the same as 1 over root 2. And look how much nicer this becomes when it comes to long division, because it becomes the thing we've evaluated, 1.412, 41423, and so on. But now we're just dividing by 2. That's amazing. We can actually start computing this now. 2's into 1 go nothing, carry 1. 2's into 14 go 7, carry nothing. 2's into 1 don't go, carry 1. 2's into 14, 7, and so on and so on. And you're only limited by the accuracy of your representation of root 2. But you can start approximating values now to the accuracy that you want. And now you can probably say, well, so what? I've got calculators for that kind of thing. That seems a bit dumb. You're right. So the only real argument, really, to rationalise denominators, so 1 over root 2 is the same as root 2 over 2, is that because, well, my only plea is that in this form, simplifications are easier to spot. And it's more of a style choice at this point. Generally speaking, mathematicians don't really like seeing irrational denominators. So it is usually just better to leave it as root 2 over 2 in this case. So okay, let's have a look at a couple more. Let's say example 2. Let's say I've got 7 over root 21. So how will I rationalise that? Well, I'll times by root 21 over root 21 again. So when there's only a single term on the bottom, I'll just leave it as that. Oops. So 7 times root 21 is 7 root 21, and then root 21 times root 21 is 21. The 7 and the 21 cancel, so this becomes root 21 over 3. Yeah, decent. However, there's a little caveat to that. Sometimes there's other nasty things. Let's say I've got 1 over the square root of root 2 minus 1. Now to solve or rationalise these things, we've got to make use of a property of a squared minus b squared is a minus b times by a plus b. Now this is really important. What it's saying is if I want to square both of the numbers, I have to multiply by what's called a conjugate. Okay, so I have a minus b in this case, where a is root 2 and b is minus 1. So if I multiply by root 2 plus 1 top and bottom, this is still 1, remember, because it's the same top and bottom. Then I've got 1 times all this, so 1 times root 2 is root 2, 1 times 1 is plus 1, all over this squared, which is 2, minus the other thing squared, which is 1, and 2 minus 1 is 1, so the result just becomes root 2, plus 1. Okay, we're going to look at some more complicated examples now. It's been 40 minutes or so. If you want to just test yourself, see if you've been absorbing the things so far, I suggest you pause the video now and give it a whirl, because I'm about to do them in a second. And in actual fact, I'm going to do them in red. So, okay, root 75. Well, that's 25 times 3, which is 75. So this is 5 root 3. 3 root 48 is 3 lots of root 48 over 48. And the 3 and the 48 cancel. So that's 16 on the bottom. And, should I have done that? Well, root 48, what's the largest square goes into that? That's 16 times 3. So that's 4 root 3 on the top. So the 4 and the 16 will cancel. So it's root 3 over 4. Yeah, makes sense. 7 root 27, or 27 is 9 times 3. So that'll be 3 root 3 times 7 is 21 root 3. And root 240. Okay, so it's 40 times 6. Let's see, 240, so 40 times 6 is 2 times 3, 40 is 2 times 20, 20 is 2 times 10, 2 times 5. Okay, so I've got 2, 2, I've got another 2, 2 there, so it's 4 times 15. Whoa, yes, 4 root 15. Because it's 16 times 15. Yeah, okay, so that's 4 root 15. So, let's tidy all this up. Root 3 over 4. Okay, so how many root 3s have I got? Well, I've got 5 there plus 21, so it's 26 root 3, but minus a quarter. So 26 times 4. It's 26 minus a quarter, lots of root 3, and then I've got a solitary 4 root 15 over here. The root 3 and root 15, just going to have to leave it as that, you can't add them. Right, 26, well 4 20s, it's 18, 4 seconds, 104. So that's going to be 103 over 4, lots of root 3, plus 4 root 15. Final answer. Okay, so 7 minus root 3 over 2 minus root 2. Let's rationalise that. So we're going to be timesing by 2 plus root 2, top and bottom. On the bottom, we're going to have 2 squared, which is 4, minus root 2 squared, which is 2. 4 minus 2 is 2. On the top, we'll have 7 times 2, which is 14. 7 plus root 2 is plus 7 root 2. Minus root 3 times 2 is minus 2 root 3. And minus root 3 times plus root 2 is minus root 6. So there's absolutely nothing we can do to that to simplify it. We could divide each term by 2, so 14 over 2 is 7, plus 7 over 2 lots of root 2, minus 2 root 3 over 2, which is going to be minus root 3, and then minus a half root 6. No, that's pretty much what it's going to be. Right, next one. Okay. Now this looks a bit saucy, but what we're going to need to do is rationalise the denominator twice. It's a bit annoying. So if I let 2 minus root 3 equal to A and root 5 equal to B, then what I've got is A plus B. So I'm actually going to try and multiply by 2 minus root 3 minus root 5 all over 2 minus root 3 minus root 5. So what am I going to get? On the bottom, I'm going to get 2 minus root 3 squared minus root 5 squared. So I'm definitely going to get a minus 5. And then 2 minus root 3 squared was 2 minus root 3 times 2 minus root 3. 2 times 2 is 4. Root 3 times root 3 is 3. Minus minus becomes plus. And then minus 2 lots of 2 root 3 is going to be minus 4 root 3. So actually, 4 plus 3 is 7 minus 4 root 3. So I've actually got 7 minus 4 root 3 minus 5 on the bottom. And you're probably thinking, oh God, that hasn't done it. Well, if you think about it, I've got a root 3 there and a root 5 there. And by doing that, I now only have one surd. So after all this, I'm just going to have to do it all again. So at the top, I'm going to have 4 plus root 3 times by 2 minus root 3 times minus root 5. Now I'm not going to expand that just yet. I'm going to leave it all to the end. Because now, if I tidy up 7 minus 5, that becomes a 2. Okay, so I'm going to multiply this by 2 plus 4 root 3 over 2 plus 4 root 3. Again, let this be one thing, that the other. 2 squared is 4, minus 4 squared is 16, times 3 is 48. So 4 minus 48, that looks like negative 44. So this becomes all over negative 44. And then it becomes 2 plus 4 root 3 times by 4 plus root 3 times by 2 minus root 3 minus root 5. God, that's a mouthful. Okay. So, pro trick, I'm going to take this negative sign out and times this by minus 1, so they cancel. So this becomes 2 plus 4 root 3 times by 4 plus root 3. And then if I take a minus 1 out as a factor here, that becomes root 5 plus root 3 minus 2. And then this is all over 44. Oh boy. Okay. Now, how to factorise things fairly speedily. What I'm going to do is I'm going to try and just do... Okay, I'm going to take 1 out of 44 out as a factor. That's fine. Now I'm going to do the numbers. How am I going to get the numbers? Well, I'm going to get 2 times 4 times minus 2. That's one way of getting numbers. So 2 times 4 times minus 2 is going to be minus 16. Another way of getting numbers. Well, if I do 2 times this 4, then it had to be with the minus 2 at the end. I can't do surds, that's not going to work. So what about 2 with root 3, and then what must I multiply root 3 by to get a number? That must be root 3 again. So 2 times root 3 times root 3 is 2 times root 9, which is 2 times 3, so that becomes 6. And that's exhausted it for the 2's. Now what about 4 root 3? Well, I could do 4 root 3 times 4 times that root 3, which is essentially going to be 4 root 3 times 4 root 3, which is 16 times 3, which is plus 48. And then I've got 4 root 3. I can't times by that 4 because I've exhausted that. What about the root 3? Well, then I have to do an integer there. So 4 times root 3 times minus 2 is going to be 4 times 3, which is 12, minus 2, which is minus 24. And now I've exercised all the number terms. Now, what about the root 3 terms? I'm hoping you can see that you're either going to get numbers, you're going to get root 3s, you're going to get root 5s. So we've done all the number terms. Let's try the root 3s. So I could do 2 times the root 3 times that number. So that's going to be minus 4. Well, let's put the root 3 in front. So plus root 3 of minus 4. Then what? Well, 2 times that 4 times root 3. It's going to be 8 lots of root 3, so plus 8. I think I've exercised all the 2's now. And then 4 root 3 will have to be the number and the number. So 4 root 3 times 4 times minus 2 is going to be minus 16 root 3. And then I think there's one more combination left. If I have 4 root 3 times the other root 3. So it's going to be 3 times 4, which is 12 root 3. Okay. I think that's it. Yep. And then, where are the root 5 terms going to be coming from? So let's say I add plus a root 5. So I'm going to have root 5 times all of this thing. Well, if I expand that out, 2 times 4 is 8, and 4 root 3 times root 3 is going to be 4 times 3, which is 12, so it's going to be 20. And then 4 root 3 times 4 plus 2 root 3 is going to be 16, it's going to be 18 root 3. And then that's it, isn't it? Yeah. Okay, so let's tidy all this up. So I've got 1 over 44, lots of. Okay, minus 16 minus 24 is minus 40, plus the 48 is 8, 8 plus 16 is 14. Minus 4 minus 16 is minus 20, but then the 8 and the 12 will cancel. Oh, that's weird. And then I'm going to have plus 20 lots of root 5, plus 18 lots of root 3 times root 5, which is root 15. Something like that. Interesting. There's probably ways that you've done it. Maybe I've made a mistake. Don't think so somehow. The method was right. You had to rationalise the denominator twice. So a cheeky look. So, what software would I use for checking something like this? Well, Wolfram Alpha is pretty decent. The only thing you have to be careful of with Wolfram Alpha is you have to be very, very precise. I mean, you will have to whenever you're typing things in anyway, but it gets a bit finicky if you don't leave things in the form that it's used to. So 4 plus square root 3 all over 2 minus square root 3 plus square root 5. Things. Ooh, I've got a minus 8 root 3 popping out from somewhere. I made a mistake. Okay, it was the root 3's. Where did I go wrong with the root 3's then? Let's step back in time. So 2 times by 4 times that root 3 is the 8. I've got that. And then 2 times the root 3 times the minus 2 is minus 4. So I got that one. 4 root 3 times 4 times minus 2. Oh, you silly boy. 4 times 4 is 16. Minus 2 is minus 32. and then if I do that root 3 and that root 3, it's going to be 3 times 4. Yeah, okay, it was here. 8 and 12 is 20, minus 36, that's minus 16. So this would have actually been minus 16 root 3. And then clearly 14, 20, 18 and 16 are all divisible by 2, so I can take that 2 out, so it becomes 1 over 22, lots of 7, and now minus 8 root 3 plus 10 root 5 plus 9 root 15. There you go, that's correct. Yeah, it's very easy to make mistakes there. It happens. Yeah. Cool. Right. So, next up, indices. Now, you've probably seen this stuff already, but here's the Indice Rules. So, whenever you multiply, now I've just written x here, but this essentially is called the base. And the power up here, this is called the index, could be the exponent, power, it's various different things you can call it, but I've tried to color code it so you can see the purple operators and then the results, what happens with the red. So, okay, what am I babbling on about? Fine. If I've got a number or a variable multiplied by the variable again, then all I need to do is add the powers together. So that's essentially what rule 1 is saying. Rule 2 is saying if I divide the same base, then I subtract the powers. Rule 3 is saying if I have a negative power, that's the same as 1 over x, well, that variable to a positive power. Rule 4 is saying if I have a fractional power, that's when surds come in, so that's the link there. And 5 is more of a giveaway. As long as that variable is not 0 itself, anything to the 0th power is just 1. Okay, so there's various things I could comment on here. Let's say I've got capital A, lots of that, and capital B, lots of that, so an A there and a B's there. Then the rule there would be AB. You multiply them together. If I've got A and B there, where they're just constants, then this would be A over B, so that would be A over B here. If I've got A there, then this will be 1 times A, which goes there. And then if I've got A lots of this thing, then this is A lots of the whole thing there, or A lots of the whole thing there. And then similarly, A lots of x naught is just going to be A. Okay, now I'm going to show you something else. These are called logarithms. And you're probably thinking, if you're a teacher or whatever, whoa, why are you showing them this? You're going to blow their minds. Okay, what I'm going to do, okay, just take a side note. I'm going to show you these 3 numbers, and we're going to play around with them for a little bit. So 2, 3, and 8. So, how many ways can you juggle these 3 numbers so they equally to each other? And you're not allowed to use any other things. So, example, if I've got 2 cubed, that is 8. That's fine. And then if I have the cubed root of 8, that's 2. So if you think about it very carefully, 8 is the subject on that one, 2 is the subject on that one, but what would an equation look like, or an identity look like, when 3 is on its own? Over here. How can I use 2 and 8? And the way it works is we say log of base 2 of 8. That looks a bit funny, but what we're essentially saying is 2 to the what power is 8. That's how logs work. And if you look at your calculator, somewhere in the middle row, you can actually find an log button. So let's have an example of that maybe. Let's say I've got log of base 5 of 25. So I'd like to know what log base 5 of 25 is. Well, that's easy. 5 to the power of what is 25? Well, that's just 2. And you can evaluate this if you just look on your calculator and find the log button. And generally speaking, it's log with a little rectangle and a big rectangle. I forget which one's shaded in or what, but it's a button looking like that, and you use your up, down, left, right buttons to navigate. Okay. Why is this useful? Because sometimes you've got something like this, 2 to the power of x equals 5, and you have no idea. You've got no idea what that value of x is. Well, now, what do you know? You know the x root of 5 is 2, and you know that log base 2 of 5 is x. And using this identity, you can quite easily work out on your calculator what that value is. So that value is, now I'm using the Casio FX CG50 here, and I must admit I'm not entirely obvious. There it is. Log base 2 of 5. So apparently this spits out a value of 2.321 and stuff. And if you're asked to give that value to a couple of decimal places, you can, and everything's fine. So, okay. What does that mean? Well, I'm going to put the log rules side by side with the indices rules. So I'm hoping you can see the analogy here. Let's put that to a side. Okay. Let's think about it. Just like in rule 1, when you added the... Let's get rid of all these A's and stuff. Maybe that's confusing it a little bit. So it's very much like the reverse. What do I mean by that? Well, let's look at rule 1. Do you see how when we added the powers, that meant I multiplied the bases? Or here it's the other way around. When I add the logs, I multiply the bases. There's a bit of an analogy there. So I'm adding the logs or the powers. That's just going to add the bases. And similarly, when I divide the bases, that's going to be a subtraction of logs, because it's a subtraction of powers over here. And then for rule 3, if I've got a negative power, a negative log, that's going to be a division of the base. Not quite so analogous here, but a log rule is stating, well, maybe you can figure it out for yourself. And for part 5, clearly, when you have x to the power 0, you get 1. Same here, x to the power 0 is 1. Okay, there's a bit of esoteric knowledge as well, and this is called change of base. Get into that kind of thing. So what he's saying is if I've got a problem that's, let's say it's log base 2 of 4, and I want to change from a log base 2 to log base of something else. Let's say I want it in terms of log base 5. Then it would be log base 2 of 4 is the same as log base 5 of 4 over log base 5 of 2. And in both cases, that's just going to be 2. But yeah, if you've got some weird demented wish of trying to change the base of something, that's totally fine. I'll be honest, it's a bit rare, it doesn't come up. Most of the time, if you've got these log rules down, I suggest you copy them down. I'm going to go through some examples of how they work. But yeah, it's probably going to be new knowledge for you if you're in year 10, year 9, year 11. So, let's have a recap. So if you want to pause it, give yourself 20 seconds, 30 seconds or so. This should be fairly easy. It's almost like revision of GCSE. So write down the value of 125 to the third. Well, this is the same as the cubed root of 125. Remember that fractional powers mean the roots, and the cube root of 125 is 5. And then find the value of 125 to the minus 2/3. Well, that's 1 over the cubed root of 125, and then square all that, so that's the same as 1 over 5 squared, which is 1 over 25. If you've written 0.04, you know, stop being silly. We prefer fractions when we're dealing with pure maths, but never mind. I mean, it's the same deal. Okay, log question. You're probably thinking, okay, how do we deal with logs? So, given that y equals log base 3 of x, find expressions for y in terms of log base 3 of x over 9. Okay, so first question you're asking yourself, is there a rule you've just learned where it's something divided by something? Well, yeah, we just backtrack up to our rules, and we've got that. The rule is when you've got something divided by something, then that's the log of one minus the log of the other. So note we know this, so that's okay. So this can be written as log base 3 of the top one minus log base 3 of the bottom one. Now let's have a think. Well, log base 3 of x, this thing, we're told is y, so that's y. And 3 to the power of what is 9? Well, that's 2, so that becomes y minus 2. So that actually wasn't too bad. Okay, next one, log base 3 of root x. And the way to deal with this is you rewrite this as log base 3 of x to the power half. Have you seen a rule where you've got something to the power something in a log? Yes, you have. There it is. And you've got a to the power b. What does that mean? It means you can bring that b down as a factor. That b goes whoop and out to the front. So what do we do here? It means that is the same as 1/2 of log base 3 of x. Well, log base 3 of x we know is y, so it's half of y, so the answer is y over 2, or half y. So yeah, that wasn't too bad. It's just like testing your knowledge of log rules, dealing with stuff like that. Wasn't so bad. Okay, next bit. Answer this question without use of calculators and show all you're working. Okay, rationalising denominators again. Cool. If you want to pause it, try it for yourself. Okay, to go through this, it's very simple. We're going to multiply by 2 root 2 plus root 6, top and bottom. 2 root 2 plus root 6. And this is going to give, well, 2 root 2 squared is 8, and root 6 squared is 6, so 8 minus 6, that gives a 2 on the bottom. 4 times 2 root 2 is 8 root 2, and 4 times root 6 is plus 4 root 6. 8 and the 4 both are factors of 2, so I can divide by 2 top and bottom to get 4 root 2 plus 2 root 6. I noticed that 4 and 2 have common factors of 2, and root 2 and root 6 both have root 2 as a factor. So 2 root 2 times what is 4 root 2, well that's 2, and 2 root 2 times what is 2 root 6, well that's root 3, and that's exactly what we wanted. So that was easy. Okay, next one. Show that that is that. Cool. So simplify root 27. That's 3 root 3. These should be nice and easy now. Root 21 is root 3 times root 7. But when we're timesing by this other root 7, that becomes 3 root 7. And then minus, and 6 root 3 becomes 6 root 3 over 3, because we've multiplied top and bottom by root 3. Oh, you silly boy. Root 7 times root 7 is 7, so that's 7 root 3. Silly boy. 6 over 3 cancels to a 2. And what do we have? 3 root 3 plus 7 root 3 is 10 root 3 minus the 2 root 3 does indeed equal 8 root 3. Okay. Ooh, given that a and b are positive constants, solve these simultaneous equations. Okay, so although I'll pause it, have a go, give yourself about 4 or 5 minutes. I mean, you'll either spot it straight away or you'll struggle for a while. If you're trying some madness, don't. You can almost spot what you need to do here if you've got your log rules down. Anyway, let's crack on. So if a times b is 25. Now what's a log minus a log? And they have to be the same base, which they are, so that's fine. That becomes log of 4 of a over b equals 3. And what this is saying is 4 to the power 3 is a over b. So that means 4 to the power 3 is a over b. And 4 cubed is 64. So now we have a over b equals 64. Right, now the trick to this one is you notice that 25 is 5 squared and 64 is 8 squared. And then what happens with AB and A over B? I mean, you could make one of them the subject and set up simultaneous equations, or sorry, a quadratic equation, or you can just spot that if you multiply these two things together, AB multiplied by A over B is just 5 squared times by 8 squared. Well, AB times A over B, the b's cancels, A times A is A squared, and 5 squared times 8 squared is going to be 40 squared. And if A squared is 40 squared, A is the positive or negative root of 40 squared, which is 40. Now, little subtle point that I didn't really talk about with logs, and it should have really been implied. You cannot, let's say I've got log of, let's say a number x, doesn't matter, and let's call this a minus k, for example. This you cannot do. You cannot take log of a negative number. You can, but there's no real solutions. Okay, why is that? Well, let's try it. Let's say log base 2 of minus 4 equals, let's say, x. Well, let's rewrite that. That means 2 to the x equals minus 4. So what does that mean? It means how many times do you have to multiply 2 by so that you get negative 4? And there's no solution to that. There's no real solution. So that's you can't do it. So if I go back to the question. So because a was inside the log, a can't be negative. So if a can't be negative, a must be the positive root, which is 40. And now let's think about it. Well, if a is 40, then according to this equation, then 40 over b equals 8 squared. If I divide by 8 both sides, then 5 over b equals 8. So then if I multiply by b and divide by 8, b is 5/8. So a is 40 and b is 5/8. Interesting. There you go. Okay, now when we're talking about logs, this is the last chapter I want to talk about today. I know I've been banging on for a good hour and a bit, but I don't expect you to watch the entire episode, this thing in one go. I mean, if you want to, that's totally fine, but I completely understand. This is the last topic I wanted to talk about today, and I'm introducing you to a new set of numbers. Okay, and at the moment, really, real numbers. So what is the real numbers? We define real numbers, the set R, this italicized R, and now essentially it maps X such that X squared is always greater than or equal to 0. Okay, What does that mean? It means that if I have a number line like this, there's 0. I can have any number on this line going to positive infinity that way. I could have any number going to negative infinity going to that way. I can pick any number on this line. It's totally fine. It also means that if I take any number and I square it, I'm going to get a positive number back. Any number that satisfies this is a real number. So minus 4. Okay, that's going to be 16, positive 16, that's totally fine. 0, well that's just 0 and that's okay because I'm allowed to have greater than or equal to 0. Minus 3.27 recurring. If I square that, then yes, that's positive, that's totally fine. If you place a pin anywhere on this real number line, then you'll be fine. What's a complex number? This is interesting. So, as you probably guessed, if x squared is always greater than or equal to 0, then what about numbers where x squared is less than 0? For example, x squared might be equal to minus 1. That's negative. So the way we get around this is to say that x is plus or minus the square root of negative 1. If you try and do this in your calculator, it'll say math error. Although if you've got a decent calculator and you put it in complex mode, it'll actually give you plus or minus I. And that's the main takeaway from this chapter, is that I is the square root of minus 1. Okay, and the way we're going to get around this whole thing is that whenever we deal with square rooting negative numbers, we're going to use our knowledge of surds to hopscotch this and use I instead. So say for example I've got something like this. Let's say I've got the square root of minus 36. Well, that's the square root of 36 times by the square root of minus 1. I know what 36 square rooted is, that's 6. I know what the square root of minus 1 is, that's going to be my complex number, my imaginary part I. So the square root of minus 36 can be just written as 6i. Now, it's I for imaginary, and complex numbers are denoted by z. No, they're not. Jeez, that's terrible. They're denoted by c, complex. Okay, and you're probably thinking, okay, imaginary, complex, make up your mind. Well, it's a little bit more technical than that. A complex number, and traditionally we use little z for that, is one that is made up of a plus I lots of b. And we say this a part is the real part, and that's essentially just like the numbers that we're used to, and we're saying this bi, this is the imaginary part. And that's not to say that it doesn't exist, but it's imaginary in terms of we haven't evaluated what the square root of minus 1 is yet. And technically, A and B are still members of the real number line. So for example, I could very much have Z1 is just 2 plus 3i. That's okay, that's a complex number, that's totally fine. I could have Z equals 3. That's okay, it's a complex number. I mean, it's a real number, but you know, there's no imaginary part, but it could be expressed as a complex number. Z3, I don't know, let's have 2i. This is a complex number, it has no real part, strictly an imaginary part. That's totally fine. Okay, so before we crack on with complex numbers, there's a couple of things I wanted to talk about. One, this introduction of Euler's number. Now it's spelt Euler, E-U-L-E-R, but it's pronounced Euler, like oil spill, Euler. Right? German mathematician. You want to Google him, know more facts about him. Incredibly smart guy. We owe quite a lot in mathematics to him. And essentially, this E number, his constant, Euler's constant, is approximately 2.71828 and so on. But it's very much like pi in terms of it's irrational, it's transcendental, it doesn't have a finite decimal expansion. It just keeps on going without a pattern. We don't know what it is. And if I was to plot y equals e to the x, it's such a beautiful function because it kind of looks like this. It spikes off to infinity to the right, and it dies off slowly, and it doesn't quite touch the x-axis. Now, why is this brilliant? Because if I plug in, let's say, the x value of 3, doesn't matter what value I pick, but let's say 3 for some example. If I trace this up to here like that, then the y value here is e cubed. But what's beautiful about that is the gradient at that point is also e cubed. And what's also brilliant about that is the area under the curve from negative infinity up to that point is also e cubed. It's the only function where the y value, the gradient of the curve at that point, and the area under that curve, bounded by the x-axis, and that x equals that value, is the case. Absolutely incredible. We'll talk about it more in depth, but the reason I have that side note is because we're now going to be looking at where complex numbers live. Now, I talked about over here the real axis as kind of like a one-dimensional thing. You can either go left or to the right. There's only one plane of existence, left, right. Complex numbers, you kind of want to get into the idea that they are two-dimensional. The real axis is going from left to right. This is re for real. And the imaginary part going up and down is like the second dimension. And just like I said before, we can write z as some x-coordinate plus iy. So if I go back to my previous example of the complex number z equals 2 plus 3i, and how we draw that is we go along 2 in the real axis, up 3, which is there, and that'll be the point here. And if you want to, you can draw a line from the origin to that point up there. But the point is, because it's a complex number, and it's up here, this is the point 2 plus 3i, think of it as like a set of coordinates. Instead of writing 2 comma 3i, you just have 2 plus 3i. That's like where you'd label it. And this is a strictly complex number. So if I look at the real axis, this is my number line again. Any point that's off of that line, we don't see because it's not real. It's got an imaginary part. And it doesn't mean it doesn't exist, it just means it's more complicated. It's a complex number. So, why have I said all this? Well, two reasons. One, if we let z equal a real part x plus an imaginary part iy, there's no reason why I parameterized it like this. Now, what do I mean by parameter? As in like the way I've defined it. I mean, essentially what I could have done is I could have said I'm going to take an angle I've deviated from the real axis, and I'll say that this height, this radius r, which is the hypotenuse here, and then if you think about it, what is sine of that theta? Because this is a right angled triangle, it will be opposite x over hypotenuse r, which leads to, oh geez, that is terrible, that is actually terrible. It's the opposite y over r, which leads to r sine theta equals y. Then similarly, if I did cosine theta, that's x over r, which will lead to r cosine theta equals to x. And now if I look back over here, if x is r cosine theta, I times y, which is r sine of theta, I get that z is r lots of cosine theta plus I sine theta. And you're probably thinking, oh dear, that's just made it complicated. Why have you done it like so? And in actual fact, the reason why I've done it like this is because there's a very important theorem which we're going to be deriving later, when cos theta plus I sine theta is actually re to the I theta. And then this r stays the same, so it's actually z is r times e theta, ei theta. And that is incredibly powerful when it comes to complex numbers. So complex numbers, they're essentially two-dimensional numbers, and z equals r times ei theta is the way we carry them around in our pocket. And the way it works is r is the distance from the origin, and theta is the angle rotated anti-clockwise from the real axis. I is the square root of -1, and for all intents and purposes we never actually evaluate it. Okay, there's a couple of takeaways before I go over from that. Let's think about it very carefully. If I is the square root of -1, then that means I squared is -1. Then if we times both sides by I, then I cubed is -I. And then if we times by I again, then I to the 4 is -I times by I, and I times I is -1, so minus minus 1, that equals +1. And then if we times by I again, we'll get I to the 5 equals 1 times I, which is I. And then can you see what's going to happen? It's just going to loop back round again. So there's this, what's called period 4 of how the powers of I repeat itself. So if I'm ever asked to work out what I to the 8 is, I know I to the 8 is is the same as I to the 4, and I know that's the same as I to the 0, so I can just keep going with 4, so I know that's just 1. Similarly, if I've got I to the 400, I can keep working down in 4s. Well, let's make it more interesting. Let's say I've got I to the 412. No, let's make it more interesting still. Let's say I've got I to the 513. Then I can divide that by 4. 513 divided by 4 is 128 1/4. So if I divide that, if I minus 128 lots of 4, I'll be left with I to the 1, which is just I. So there's some interesting properties with how I just keeps repeating itself. Second of all, for reasons that will be explained later, we do not use degrees anymore for complex numbers. So this 0 degrees to 360 degrees, you need to delete from memory. What we actually use are radians. And this is so important. Let's go with some key facts. What are radians? Well, 0 degrees is just 0 radians, and I'll call them 0 rads. And 360 degrees is just 2 pi rads. So, in conclusion, a whole circle, that's 2 pi. A half circle, that's half of that, which is pi. A 90-degree angle, that's half of that again, that's pi over 2. A 45-degree angle, that's pi over 4. And essentially, we measure things as fractions as pi. If you look on your calculator, you can press shift and then angle setup, and you can change from deg to rads if you want to. To be honest, all the stuff we're going to be doing today, you don't actually need your calculator for this, but just please be aware that when we're working in the complex plane, we're dealing with radians. Okay, we don't use degrees. Degrees are not a silly idea, but they were just a callback to when we used to think 360 days are in the year. 360 could be divided by 4, by 3, by 2, by 5, by 6, not by 7, but by 8, by 9, by 10, not by 11, but all the nicer numbers, which it just could divide things. It just had this kind of factor prime feel about it, and it suited our needs. And then, as history progressed, we realised it wasn't 360 days, it was more like 365, and then 365.25, and then 365 and I forget what it is, 2496 or whatever it is, I can't remember. It's on the Gregorian calendars. If you Google it, it's not a whole number. Anyway. So before we crack on as well, if I wanted to say Z and find the length of it, this is called the magnitude, or the absolute value, then the absolute value of Z is just this R value. And that's really easy to compute. It's just x squared plus y squared square rooted, just by Pythagoras. That's really easy. And the argument of Z, that's also really easy. That's just the angle theta. Okay, so maybe that's quite a lot to digest. So I'm just going to go through a few examples and hopefully you pick up. If you have picked up already, give it a go what's going here. But otherwise I'm going to be going through these in just a second. Pause the video if you want to have a go. Okay, right, let's go through it. So Z1 is 2 plus 8i, and Z2 is 1 minus I. That's what I should have mentioned before. If Z is A plus B lots of I, or IB, then Z star is A minus BI. Now this is what's called the complex conjugate. And sometimes Z star, some books Z bar. It usually makes it clear in the context. But this idea of complex conjugate is going to be really helpful when it comes to dividing by complex numbers. So anyway, if you want to have a rethink and go for it, fine. So find out what Z1 divided by Z2 is. Okay, so Z1 is 2 plus 8i over Z2, which is 1 minus I. So this is irrational. So we're going to have to multiply by its complex conjugate, which is 1 plus I, top and bottom. And on the bottom, we're going to have 1 squared, which is 1, minus I squared, which is minus 1. So we've got 1 minus minus 1 becomes 1 plus 1. On the top, I've got 2 times 1, which is 2. I've got 2 times I, which is plus 2i. I've got 8i times 1, which is plus 8i. And I've got 8i times I, which is 8i squared, which is minus 8. So 2 minus 8 is minus 6. 2i plus 8i is 10i. But then I divide that all by 1 plus 1, which is 2. So minus 6 over 2 is minus 3. 10i over 2 is going to be 5i. So my answer for that is minus 3 plus 5i. So A was minus 3 and B was plus 5. Find the value of Z1, Z2 over Z2, sorry. Okay, so let's plot this on the Argand diagram, shall we? So the real part was minus 3, so I go back to minus 3, and the complex part was 5i, so I go up 5 like that. So it's this point there, so bosh, this is the radius. So it's pretty easy to see. It's going to have a height of 5 and it goes back 3. So I've got essentially a triangle, a right-angled one, which is 3, 5, and I want to find this r. So that's going to be the square root of 3 squared plus 5 squared. 3 squared is 9, 5 squared is 25, so it's going to be root 34. So the value of the modulus, the absolute value, is root 34. It's just the length of the complex number. It's gone away. Okay, the value of the arg of Z1, Z2, your answer in radians to 2 decimal places. Okay, so what is the argument? The argument is this value here. It's this. Do you remember? It's the radius. Sorry, it's the angle rotated anti-clockwise from the positive real axis. So if we call this angle here theta, then the inverse tan of opposite 5/3 will give theta. So that means the argument of Z1/Z2 is going to be pi, which is 180 degrees, remember in radians, minus the inverse tan of 5/3. So, menu, so shift, setup. Make sure your calculator's in radians. Mine wasn't, so that's a good thing I checked. And now pi, shift, pi minus, oh dear, where's my math stuff? Math, oh dear, where's my trig? Ah, there it is. Shift tan of 5/3. So apparently, to 2 decimal places, that's 2.11 radians. Okay. Yeah, moderately tricky. We get loads of these in the practice exercise, and you can always mail me for stuff. Okay, other one, if you want to give it a go. Now that I've gone through one, more than welcome. Pause the video. Okay, given that Z1 is that and Z2 is 12, that's a 12, minus 5/Z1, find Z2 in the form, okay, right, so what is 12 minus 5i over 3 plus 2i? Well, we're going to have to multiply by 3 minus 2i over 3 minus 2i. So we're going to have 3 squared, which is 9, minus 2i squared, which is 4 times i squared, which is minus 4. 12 times 3 is 36. 12 times minus 2i is minus 24i. Minus 5 times 3 is minus 15i. And minus 5 times minus 2i. Well, minus is plus, but I squared is negative. And then 5 times 2 is 10. Okay, 36 minus 10 is 26. 24 minus 15 is minus 39i. This is all over 9 minus 4, which is 13. 26 over 13 is 2. Minus 39 over 13 is 3i. So this is actually what Z2 simplifies down to. Show in an Argand diagram the point P representing Z1 and Q representing Z2. Okay, so there you go. Oops, a daisy. There you go. Right, so Z1 is 3 plus 2i, so along 3 up 2 is there, so that's the point P, which is 3, 2, so that's the real part and that's the imaginary. And then Z2 is 2 minus 3i, so that's minus 3 down there, that's 2 there, that is Q. That's interesting because they are perpendicular. Oh, that's interesting. Given that O is the origin, show that the angle POQ is pi over 2. Well, there's lots of ways of doing this. For a start, well, you can probably know that the gradient of the gradient of this line of the origin to P is 2 over 3, and the gradient of the origin to Q is, it goes down 3, 2, and since these are negative reciprocals to each other, they are perpendicular, and if they're perpendicular, the angle must be 90 degrees. 90 degrees in radians is pi over 2. The circle passing the points OP and Q has a centre at C. Okay, the complex number, centre at C. Okay, so a bit of GCC revision. If there's a circle that goes through O, P and Q, oops, like that, that is terrible. That's still bad, but never mind. Then if I know there's a 90 degrees there, then if I join a line from P to Q like that, then the centre must be in the middle from basic circle theorems. So essentially I have to find the midpoint. So if I've got one number which was what, 3 plus 2i, so that's coordinate 3, 2, and I want to find the midpoint, and then it was 2 minus 3. So what's halfway between 3 and 2? Well, that's 2.5, which is 5 over 2. And what's halfway between 2 and minus 3? Add them together. Okay, so it's minus a half. So the complex number is going to be 5 over 2 minus a half I. That is what C is. Remember, we're not dealing with coordinates. I just used coordinates to make it a bit easier. Find the exact value of the radius of the circle. Well, if I can work out what P to Q is, I just divide it by 2. So that's just Pythagoras again, isn't it? So this point here was 3, 2. This point here was 2, minus 3. This is where P was, this is where Q was. And the height is going to be 5. 2 to 3 is 1. So this is just root 26. Because 5 squared is 25 plus 1 squared is 26. Okay, so the radius is just going to be root 26 all over 2. That is the exact value of the radius. Okay, again, if you want to pause this, give it a whirl. Okay, the complex numbers Z1 and Z2 are given by that. Show them on an Argand diagram. Okay, so Z1, 2 minus I. So you go along 2, down minus I, so you're there, so that's Z1. That's minus 1i, that's 2 there, so that's my real axis, that's my imaginary. And Z2 is minus 8 plus 9, so I go back minus 8 in the real and up 9 in the imaginary, so it's up here somewhere, that's Z2. Okay. Find, showing you're working, the value of Z1. Oh, that's easy. Well, that's just the hypotenuse of this triangle here. So it's 2 along and 1 down. So 2, 1, that's R. So that's just going to be root 5. Find the arg of Z1. Okay. So you could go clockwise like that. Or you could just do 2 pi, which is 360 minus that angle. So it would be 2 pi minus the inverse tan of the opposite length, which is 1 over 2. So same deal, 2 shift pi minus inverse tan of half. So 5.82 is perfectly acceptable. Yeah, that'll do. And then Z2 over Z1, so that's going to be minus 8 plus 9i over 2 minus I, so I'm going to multiply by 2 plus I top and bottom. 2 plus I on the bottom is going to be a 5, because 2 squared is 4, minus and I squared is minus 1, 4 minus 1 is 5, minus 8 times 2 is minus 16, minus 8 times I is minus 8i, 9i times 2 is plus 18i, 9i times plus I is going to give negative 9. So minus 16 minus 9 is going to be minus 25, minus 8i plus 18 is going to be plus 10i, it's all divided by 5, minus 25 divided by 5 is minus 5, 10 divided by 5 is plus 2i. So there you go. That is that. Okay, now we're coming up to the final bit of complex numbers, and you're probably thinking, oh man, you taught me this Euler stuff, I haven't seen it yet, what's going on, man? Where's this z equals r e to the I business coming from? And here it is. So when it comes to solving indices problems, okay, in the real number line, it's relatively straightforward. I've got x cubed equals 64, and for example, and that just gives the answer x equals 4. And if I was to tell you x squared equals to 4 and x equals plus or minus 2 from that, you're probably thinking, okay, so why are there two answers? And I could probably give you some argument of, well, minus 2 times minus 2 is positive 4. What I need to get your head around is that if this number is a 3, that means there's actually 3 solutions for this equation. The problem is only one of them is real. The other 2 don't really exist. They're imaginary. Well, they exist on the complex plane. They don't exist in the real number line. That's terrible. So let's talk about what I'm saying here. So let's suppose x cubed is now a complex thing, and we're dealing it with like this. Let's say I've got z cubed equals 64. Okay, now let's think about very carefully what that means. That means, where is 64? Well, 64 is plus 0i. So on the imaginary axis and the real axis, that means we're out here at 64. And with the Euler thing, that means z cubed, Euler's identity, is that we've got 64, lots of e to the I, lots of 0. Okay, because it's 0 radians. You haven't rotated at all. Okay. But if you think about it, that's also the same as 64 e to the I, lots of 2 pi. Because I could rotate this a whole rotation round 2 pi and still be on the real axis. I could actually rotate it 4 pi. I could just keep rotating it by as many 2 pi's as I want. 6 pi, 8 pi. I could even go backwards and say minus 2 pi, minus 4 pi. The point is, if I keep rotating round, it's not going to change where I land up. I'm just going to always end up on the real axis. So really, z cubed could be e to the I, and then this could be any multiple 2n of pi. Okay, so more generally, z cubed is 64i to the 2 pi lots of n. And now here's the magic of how we solve this. I take the cubed root of everything. So I'm going to take the cubed root of 64, and then the cubed root of this is going to be e to the I 2 pi n, and then I cube root that. Now the cube root of 64 numerically is just going to be 4. And now, when I have powers of powers, I multiply them. So it's going to be e to the I 2 pi n over 3 now. Now that's really weird, because if you think about it, what's happened? I've cube rooted the numerical part of this, but I've actually divided the angle by 3. So let's think 2 pi n over 3. What are all the multiples of 2 pi n over 3? Well, n could have been 0, which means we'd have 0. And then I could have had n is 1, so that's 2 pi thirds. And then I could have had n is 2, so that's 4 pi thirds. Then I could have had n is 3, which is 6 pi thirds over 3, which is 2 pi. But then 0 is the same as 2 pi. And then if n was 4, it would be 8 pi thirds over 3. But if you think about it, 8 pi thirds is just 2 pi plus another 2 pi thirds. It's just a whole rotation plus 2 pi thirds. So really that's the same as that. This is the same as this. There's only actually 1, 2, 3 distinct angles going on here. And what are they? Well, There's one here at 4 when, you know, the argument's 0. There's another one at 2 pi thirds, which is going to be popping out over here, where that angle is 2 pi thirds. And there's another one of distance 4 away. And then there's another one popping out over here, where I go 2 pi thirds back. And if you squint your eyes, what's actually happened is I've created a circle of radius 3 and I've split it up into 1, 2, 3 equal bits, where the roots, the cube roots of 64 are actually in they're actually in 1, 2, 3 places, and only this one lies on the real number line. That's why when we cube root 64, we only see in the real axis one solution that is 4, but actually there's 4 lots of e to the I 2 pi over 3. There's 4e to the I 4 pi over 3, and there's just 4, which is e to the I 0 pi over 3, which is e to the I 0, and anything to the power 0 is just 1. So in actual fact, there's 3 solutions. And generally speaking, if I've got a power of 3, or a power of 4, or a power of 5, that means I'm going to find one what's called principal root, which is when you divide by this thing here, or you take the nth root of that, and then you're going to have the n amount of rotations. So if I wanted to solve z to the 5, that probably means I'm going to end up with a circle whose radius is a 5th root of the original thing, but the solutions split up that circle into 1, 2, 3, 4, 5 equal bits. So, bit tricky. Now, this is all bearing in mind that de Moivre's identity, which we're not going to prove, but as I expressed before, e to the I theta is cosine theta plus I sine theta. So r lots of this is r lots of cosine that, and this is z. So if you'd like to give this a go, pause it, give yourself a good 10 minutes. I suggest you draw an Argand diagram. Yeah, just give it a go. Okay, so if z cubed equals 4 root 2 minus 4 root 2i, then let's draw this on an Argand diagram. So what does that mean? We go 4 root 2 that way, we go 4 root 2 down, so it's like that. Okay, so can I write this as r lots of e to the I theta? Do I know this radius? Well, yeah, I can probably work it out because I've got a right-angled triangle where this is 4 root 2, this is 4 root 2, that squared is 32, that squared is 32, so this is the square root of 64, which is 8. So I know that z cubed is 8 lots of e to the I theta, and now I need to work out this angle. Well, you can probably tell from inspection that if that and that are the same distance, then this is 45 degrees. So what does that mean? It means we have gone, well, what is 45 degrees? 45 degrees is pi over 4 radians, remember? So we need to go a whole 2 pi and then back pi over 4. So what is 2 pi minus pi over 4? Well, 2 pi is 8 quarters of pi, so minus 1, so it's going to be 7 quarters of pi. Okay, good. Now, let's deal with this. So what's z going to be? Well, we're going to take the cube root of the 8, and then we're going to take the cubed root of EI 7 pi over 4. So that means 8 to the third is just 2. And we multiply the powers here and here. So this is e to the I 7 pi over 12. And now, if we think about it, this power was a third, right? So that means wherever that root is going to be, it's going to split the circle up into 3 equal bits. So if a whole 2 pi has been divided in 3, that means we can keep adding multiples of 2 pi thirds onto this. So here's a question. Theta, the angle, can only be between pi and minus pi. So here's 7 pi over 12. Now if we can keep adding or subtracting 2 pi over 3, I'm going to change that into 12. So times by 4, that's 8 pi over 12, isn't it? So can I add 8 pi over 12s to 7 pi over 12s? Well, that would be 15 pi over 12s. Well, 15 pi over 12s is bigger than pi, so that's not going to work. So can we go back pi over 12s? Well, yeah, 7 minus 8 is going to be minus pi over 12. So that will work. And then can I minus another 8 pi over 12? Well, yeah, well, it's going to be minus 9 pi over 12. And then if I minus another 8 pi over 12, it's going to be minus 17 pi over 12. And then 17 is bigger than 12, so it's going to be too small. So that's not going to work either. So really, there's 3 answers in that range. To any of so Z could be, what was it? 2 to the E minus I, lots of 9 pi over 12. Or Z could be 2e to the minus pi over 12, or 2e to the I, lots of 7 pi over 12. And 9 pi over 12 we can divide by 3 top and bottom to get 3/4. Okay, so we've got the answers, but it's not in the form they wanted it. They wanted it in the form r cosine theta plus I sine theta. So now we've got it in this form, this is now really easy to read out. So Z is going to be 2 lots of, 2 lots of, 2 lots of. And then for each of these we've got cosine of an angle plus I sine of an angle, cosine of an angle plus I sine of an angle, cosine of an angle plus I sine of an angle. Okay, so first one is minus 3 pi quarters. This is minus 3 pi quarters. Next one is minus pi over 12. This is minus pi over 12. And this is 7 pi over 12. And this is 7 pi over 12. Okay, so this is perfectly acceptable. The only thing I would say is later on we realise that through something called even and odd functions, that cosine of negative x is just cosine of x, and sine of negative x is just minus sine of x. And what makes that really nice is we can get rid of these negative values inside of the trig function. So that means cosine of minus 3/4 and cosine of minus pi over 12 are just cosine of the positives. But then with sine, to get rid of the negative values, we can just put minuses there. But since the question didn't specify, you could have left your answer as these. That's totally fine. Cool. Okay, well, there's another one here. Express the complex number in the form of r cosine theta plus I sine theta and solve that equation. Okay, so pause the video if you want to give yourself a chance to give it a go. But I'm going to go through it now. So let's draw an Argand diagram. So the real part is minus 2, so minus 2 is there, and the complex part is 2√3, which is up here. So it's going to be over there somewhere. And if I consider a right-angled triangle where the height is 2√3 and the base is 2, then this r value is going to be 2 squared, which is 4, square rooted, plus 2√3 all squared, which is 4 times 3, which is 12. So it looks like r is root 16, which is 4. Interesting. So that means it's going to be 4 lots of cosine of what angle plus I sine of what other angle. And the argument is going to be pretty easy. It's going to be this angle here. Okay, well, you can probably do this by inspection. But if I want this angle theta, say, where this is 2 and this is 2 root 3, then what's the inverse tan of the opposite, which is 2 root 3, over the adjacent, which is 2, which is the same as the inverse tan of root 3 over 1. Now, you might memorise this from GCSE, this is being 60 degrees, but because we're in radians, it's going to be half of a circle pi and half a circle divided by 3. So it's pi over 3. So if this angle there is pi over 3, then that means this one here is 2/3 of pi, because the whole thing is 180, or a whole pi radians. So this means it's going to be 2 pi thirds, 2 pi thirds. So there's your answer for the first part. Okay, part B, solve z to the 4 of that thing. Okay, so, well, let's deal with it. So if z to the 4 equals r e I theta, what was r? It was 4, and I, or theta, was, what was it? It was 2 pi over 3, and this equals z to the 4. So if I take the 4th root of both sides, the 4th root of 4, well, that's the same as square rooting and square rooting again, so it's going to be root 2, and then 4th rooting this becomes I to the 2 pi over 3 times 4 is 12. And 2 pi over 12 is the same as a 1/6 of pi. Okay, so actually z is root 2 e to the I pi 1/6. And because we're taking the 4th root, that means we can add or subtract multiples of 2 pi a whole term over the 4. And 2 pi over 4 is the same as half pi. So, what are all the angles if you add or subtract half a pi from pi over 6, give or take pi over 2? So let's try it. Pi over 6. If I add pi over 2, which is 3 pi over 6, then that's going to be 4 pi over 6. I haven't reached a whole pi, so I'll keep going. Add another 3 pi over 6, that's 7 pi over 6, that's too big, it's bigger than pi. If I go down from pi over 6, that becomes minus 2 pi over 6, which is okay. If I go down another 3 pi over 6, I've got minus 5 pi over 6. If I go down another 3, that's minus 8 pi over 6, and that's too small. And lo and behold, 1, 2, 3, 4. There's 4 solutions, because z is being to the power forward, and from pi to minus pi, if you think about it, pi is here, so we're going from 0 to pi, and we're going from 0 to minus pi, so that completely encapsulates one term. So one term we'd expect to find 4 answers, and indeed we do. So z is going to be root 2, lots of e to the I minus 5 pi over 6, or it's going to be root 2 of e to the minus I of 2 pi over 6, which is 1/3 of pi, or it's going to be root 2 of e to the I pi over 6, or it's going to be root 2 of e to the I 4 pi over 6 is 2 pi thirds. So there's 4 roots to this. All of them are complex, none of them lie on the real plane. Yeah, those are the answers. Oh, no, they want them in terms of r cos of blah, blah. That's okay. Well, we know how to deal with that. That's going to be root 2 cosine of the angle, which is minus 5 pi over 6, plus I times sine of the angle, minus 5 pi over 6, close brackets. This one is going to be root 2 lots of cosine of minus pi over 3, plus I sine of minus pi over 3. Next one is going to be root 2 of cosine of pi over 6 plus I sine of pi over 6. Next one is going to be root 2 of cosine 2 pi over 3 plus I sine 2 pi over 3. Okay. Well, yeah, that's it. So It's a hell of a lot there. What are we on now? 2 and a bit hours. Brilliant. So yeah, I definitely break this up into pieces if I were you. I'm probably going to timestamp the relevant bits of information, and I'll also include problem sheet to practice all this stuff. If it takes you a week or so, that's absolutely fine. I may not have explained things particularly clearly. Well, I'd love to explain again. Maybe I can attach private comments. I'll put some different videos up on YouTube as well, not ones done by me, explained elsewhere. But you have to understand, I've skipped a lot of things and I've cherry-picked certain things for you to do, but please be aware I will be going into detail of some of them at a later date when you understand a bit more. All right, thanks guys.